if you pointed a flashlight at Betelgeuse, and somehow that beam could travel in a straight line through the star from one side to the other, the light would take 59 minutes to make the trip. Not 59 minutes to reach Betelgeuse. 59 minutes just to cross through it. Light crosses our sun in 4.5 seconds. It reaches Earth from the sun in about 8 minutes. But crossing a single star, one star, in the constellation Orion takes nearly a full hour. And that is just the beginning of how absurd this thing is. Betelgeuse is a red supergiant. You have probably heard that term before, but most people hear it and picture something like a big star, maybe 2 or 3 times bigger than the sun. That is not what we are dealing with here. Betelgeuse is 764 times the radius of the sun. Not 764%, 764 times. Its diameter stretches about 7.1 astronomical units across, which means if you placed it where our sun is, its surface would blow past Mercury, past Venus, past Earth, past Mars, past the entire asteroid belt, and keep going until it reached roughly 68% of the way to Jupiter's orbit. 5 planets and a belt of space rocks swallowed, gone. Just the interior of a single star. But here is where it gets genuinely strange, because a star that enormous, something 764 times wider than the sun, you would expect it to be incomprehensibly massive. It is not. Betelgeuse is only about 16 to 19 times the mass of the sun. You could fit 446 million suns inside its volume, roughly 580 trillion Earths. But the actual stuff in there, the actual matter, weighs less than 20 suns, which means the average density of Betelgeuse is approximately 12 billionths of a gram per cubic centimeter. Astrophysicist Brian Koberlein described it as basically a red-hot vacuum and noted that the average density inside this star is comparable to the vacuum inside an insulating thermos bottle. So picture that. A sphere of near nothing stretching from the sun past Mars, glowing at 3,500 degrees, pulsating, shedding its own skin into space, and slowly dying. That is Betelgeuse, and it is only 548 light years away, which, cosmically speaking, is right next door. Close enough that when it finally explodes, and it will, the supernova will be bright enough to cast shadows on Earth at midnight and remain visible in full daylight for months. But we will get to that. First, you need to understand what you are actually looking at when you look at Orion's shoulder, because it is not just big. It is a dying thing, and the way it is dying tells us something extraordinary about how the universe builds and destroys its largest creations. Let us start with what we actually know about its size, because even that turns out to be more complicated than it should be. The best current estimate for Betelgeuse's radius comes from a 2020 study by Meredith Joyce and her collaborators, who combined evolutionary modeling, asteroseismic analysis, and hydrodynamic simulations to land on 764 solar radii. In kilometers, that is roughly 531.7 million. In astronomical units, 3.55. But that number is not settled. Other teams have gotten different answers, and the disagreements are not small. Dolan and colleagues in 2016 measured 887 solar radii, plus or minus 203. Mittag and collaborators in 2022 proposed a smaller value, around 640, And when you observe Betelgeuse at millimeter wavelengths using ALMA, the Atacama Large Millimeter Array, the star appears to have a radius of roughly 1,400 solar radii, about 6.5 astronomical units. That would put its surface past Jupiter. So why can we not agree on how big this thing is? 4 reasons, and they all compound each other. First, Betelgeuse does not have a surface, not in the way you think of a surface. There is no hard edge, no boundary where star ends and space begins. The outer atmosphere just gradually fades into the surrounding vacuum, getting thinner and thinner until it becomes indistinguishable from interstellar space. Different wavelengths of light come from different depths in that atmosphere. So a telescope looking in visible light sees one size, and a radio telescope sees a much larger one. Second, the star pulsates. It physically expands and contracts over cycles of roughly 420 days, meaning the actual radius changes depending on when you measure it. Some estimates suggest the diameter can vary by as much as 60% over a full pulsation cycle. Third, limb darkening makes the edges of the disk appear to fade rather than stop, complicating any attempt to define where the star ends. And fourth, circumstellar dust shells, material the star has already shed, create a haze around the photosphere that blurs the boundary even further. And then there is the distance problem. We are not even sure how far away Betelgeuse is. The original Hipparcos measurement in 1997 placed it at about 427 light-years. The revised catalogue in 2007 pushed that to around 500, give or take 65. Radio parallax measurements from Harper and collaborators suggested 643, plus or minus 146. A combined analysis in 2017 produced about 724. Joyce's 2020 modelling settled on 548. The current best guess is somewhere between 500 and 650 light-years. This matters because every measurement of the star's physical size depends on knowing the distance. If it is farther than we think, it is bigger. If it is closer, it is smaller. The range of possible distances produces radius estimates that vary by nearly a factor of 2. You might wonder why Gaia, the European Space Agency's precision astrometry satellite that has measured the distances to nearly 2 billion stars, has not just settled this. The answer is embarrassingly simple. Betelgeuse is too bright. Gaia's detectors saturate for anything brighter than about 6th magnitude, and Betelgeuse typically shines at magnitude 0.5. The most precisely measured star mapping satellite in history literally cannot look at one of the most important stars in the sky without being blinded by it. But even with all these uncertainties, the scale of the thing is undeniable. So let us put it in terms that actually mean something. If you dropped Betelgeuse into the center of our solar system, replacing the Sun, the first thing that would happen is nothing. Mercury, orbiting at 0.39 astronomical units, would find itself roughly 11% of the way from the center of the star to its surface. Not near the surface, deep inside it, Mercury would be embedded in stellar material, surrounded by hot, tenuous plasma at thousands of degrees. It would not survive. It would not even have a chance to not survive. It would simply be inside a star. Venus, at 0.72 astronomical units, would be at about 20% of the way from center to surface. Same situation. Earth, at 1 astronomical unit would sit 28% of the way out. You, reading this, would be inside Betelgeuse. The planet you are standing on would be roughly a quarter of the way from the center of a dying star to its photosphere, immersed in gas so thin it would technically qualify as a laboratory vacuum on Earth, but so hot that nothing solid would exist. Mars, at 1.52 astronomical units, would be swallowed at 43% of the stellar radius, still deep inside. The asteroid belt, with Ceres orbiting at about 2.77 astronomical units, would be consumed at 78% of the radius. Even the asteroid belt, the vast ring of debris between Mars and Jupiter that takes years to cross at spacecraft speeds, would be just another layer of Betelgeuse's interior. Jupiter is the first survivor, but barely. At 5.2 astronomical units, it would orbit about 1.65 astronomical units beyond Betelgeuse's optical surface. It would be outside the star, technically, but bathed in radiation intense enough to strip its atmosphere over time. And if you use the higher radius estimates, the ones from certain interferometric studies or ALMA observations, Jupiter does not survive either. At 1400 solar radii, Betelgeuse's surface would extend past 6.5 astronomical units, swallowing Jupiter entirely. At that size, Saturn, orbiting at 9.54 astronomical units, would be the first planet to escape. The European Southern Observatory has published annotated images stating that Betelgeuse would engulf all 4 terrestrial planets and even the gas giant Jupiter. Think about what this means for a moment. Our entire inner solar system, everything from the Sun to the asteroid belt, every planet we have ever set foot on or sent a rover to, would exist inside the body of a single star. Not near it, inside it. The distance from here to the Sun, the yardstick we use to measure everything else in the solar system, would be less than a third of the way from Betelgeuse's center to its surface. The distance from here to Mars, which takes our best spacecraft 7 months to traverse, would be swallowed before we even reach the halfway point. And the experience of being inside this star would be paradoxically serene and lethal at the same time. At Earth's orbital distance, the density of the stellar material would be negligibly low. You would not feel any resistance, any pressure, any sense of being inside something. The gas around you would be thinner than the best vacuum chambers on Earth, but the temperature would be several thousand degrees. Everything would be bathed in infrared radiation, and gravity, which at the surface of the Sun pulls at 28 times Earth's gravity, would at this depth within Betelgeuse be pulling mostly inward toward the core, drawing the tenuous material slowly, inexorably downward toward the burning shells, where the real physics is happening. And here is the part that bends your mind. Despite containing 580 trillion Earths worth of volume, Betelgeuse's average density is so low that if you could somehow scoop out a cubic meter of its average material, it would weigh less than a cubic meter of the best laboratory vacuum we can create on Earth, 1,000,000 times less dense than air. You would not even know you were inside a star, at least not from the density of the gas around you. You would know from the temperature, though. That would be unmistakable. Let us make the scale even more concrete. A commercial airplane flying at 900 kilometers per hour around Betelgeuse's equator would need 424 years to complete one lap. 424 years. That is a journey from Shakespeare's era to today. A car driving at highway speed across the diameter would take 1,214 years, a trip stretching back to the Viking Age. Even the Voyager spacecraft, one of the fastest objects humanity has ever built, traveling at 17 kilometers per second, would need about 2 years just to cross from one side of Betelgeuse to the other. 2 years inside a single star. So how did this happen? How does a star get this big? Because Betelgeuse was not always like this. In fact, when it was born, it looked nothing like the bloated red monster we see today. Understanding how it got here is one of the most beautiful stories in all of physics, and it starts with a paradox. The more massive a star is, the shorter it lives, and the reason for that reveals something fundamental about the way gravity and nuclear physics negotiate the existence of every star in the universe. Betelgeuse was born roughly 8 to 10 million years ago, which makes it absurdly young by stellar standards. Our Sun is 4.6 billion years old and is not even halfway through its life. Betelgeuse has burned through almost its entire existence in less than 1/4% of the Sun's current age. It was born as a blue-white O-type main sequence star, one of the hottest and most luminous classes of star that exist. Surface temperature, somewhere between 25,000 and 35,000 Kelvin. Luminosity between 10,000 and 50,000 times the Sun. It was brilliant, compact, and burning through hydrogen at a rate that made its death inevitable within a few million years. The key is the CNO cycle. Stars like the Sun fuse hydrogen through the proton-proton chain, a relatively slow process where individual protons gradually combine to form helium. But for stars above roughly 1.5 solar masses, a different mechanism dominates. Carbon, nitrogen, and oxygen atoms in the core act as catalysts, shuttling protons through a cycle that produces helium much more efficiently. The CNO cycle's energy production is extraordinarily sensitive to temperature. It scales roughly as temperature to the 16th power, meaning a small increase in core temperature produces a massive increase in energy output. This extreme sensitivity concentrates all the energy generation into a tiny, blisteringly hot, convective core. And this is where the clock starts ticking. Because in the Sun, hydrogen depletion happens gradually, starting from the center and working outward over billions of years. But in a massive star with a convective core, the fuel is stirred. Convection mixes the material throughout the entire core uniformly, meaning hydrogen is consumed everywhere at the same rate. When it runs out everywhere at once, not gradually, not over hundreds of millions of years, all at once, a sudden energy crisis. When the hydrogen in Betelgeuse's core was exhausted, the core was left as a ball of inert helium. No nuclear reactions, no radiation pressure to push outward against gravity. So the core did what any unsupported structure does under gravity. It contracted, and as it contracted, it heated up. Gravitational compression converted potential energy into thermal energy, raising the temperature of the layers just outside the helium core. Eventually, those layers got hot enough for hydrogen to ignite in a thin shell surrounding the dead core. Shell hydrogen burning. But here is the thing that makes red supergiants possible. Something called the mirror principle. When the core contracts, the envelope, the vast outer layers of the star, expands. This is not intuitive. You would think a contracting core would pull everything inward, but the physics works the other way. A 2024 study by Yu and Chen laid out the mechanism precisely. As the hydrogen-burning shell's outer boundary moves inward, the local gravitational acceleration increases. To maintain hydrostatic equilibrium, the pressure gradient has to steepen, but the pressure at the burning shell is fixed by nuclear conditions. The only way to resolve this is for the envelope's density to decrease, which forces expansion. It is not that energy is being pumped outward, it is that the structural requirements of equilibrium physics demand that the star inflate. And inflate it did. The envelope expanded enormously, cooling as it went. When the surface temperature dropped below about 5,000 to 6,000 Kelvin, something important happened. The opacity of the gas increased dramatically. Negatively charged hydrogen ions and molecular absorption started trapping radiation much more efficiently, which triggered deep convection throughout the entire envelope. The star ballooned to the Hayashi limit, the coolest temperature a star of that luminosity can possibly have while remaining in hydrostatic equilibrium. It settled on the far right edge of the Hertzsprung-Russell diagram as a red supergiant, blue-white furnace to red giant. Not over billions of years, over maybe a few tens of thousands. Meanwhile, the core kept contracting and heating. When it reached about 100 million Kelvin, helium ignited. 3 helium, 4 nuclei fusing into carbon-12 through the triple alpha process. In lower mass stars, this ignition happens violently, something called the helium flash, because the core has become degenerate and cannot regulate its temperature. But for massive stars like Betelgeuse, the core temperatures hit the helium ignition point before degeneracy sets in. So helium burning begins gently, stably. No flash, just a smooth transition to a new fuel source. But helium burning is less efficient than hydrogen burning, and each subsequent fuel burns faster than the last. This is the accelerating clock toward oblivion, and the numbers are staggering. For a star of roughly 20 solar masses, hydrogen burning lasts about 8 to 10 million years. Helium burning lasts about 1 million years. Carbon burning lasts roughly 1,000 years. Neon burning, about 1 year. Oxygen burning, months. And silicon burning, the final stage before core collapse, lasts only days. Each phase is shorter because each reaction releases less binding energy per nucleon. But from carbon burning onward, there is an additional accelerant: neutrino losses. At the temperatures required for carbon fusion and beyond, the core produces enormous quantities of neutrinos. And unlike photons, neutrinos do not interact with matter. They fly straight out of the core at nearly the speed of light, carrying away energy that the star never gets to use. The star has to burn fuel faster and faster just to replace what the neutrinos are stealing. It is like trying to heat a house with the windows open in a blizzard. The colder it gets, the more fuel you burn, the more heat escapes, the faster you have to burn. The result is a star with an onion layer interior, concentric shells of progressively heavier elements, each with its own fusion reactions happening at different temperatures. If Betelgeuse has developed all its shells, the structure from outside in would look something like this: a massive convective envelope extending to 3.55 astronomical units, almost entirely hydrogen and helium, at about 3,500 Kelvin, then a hydrogen burning shell at 20 to 50 million Kelvin, converting hydrogen to helium via the CNO cycle, then a helium burning shell at 100 to 200 million Kelvin, running the triple alpha process, then potentially a carbon burning shell at 600 to 800 million Kelvin, then neon burning at 1.2 to 1.5 billion Kelvin, then oxygen burning at 1.5 to 2.3 billion, then silicon burning at 2.7 to 3.5 billion. And finally, if the star has reached its end stage, an iron-nickel core at 3 to 5 billion Kelvin, roughly the size of Earth, where no further exothermic fusion is possible. Iron is the end of the line. Fusing iron absorbs energy rather than releasing it. When the core becomes iron, the star has written its own death sentence. The scale contrast within this structure is almost impossible to grasp. The entire nuclear burning core, all of those concentric shells where the actual physics of element creation is happening, occupies a region perhaps a few percent of a solar radius across, a tiny ball of nuclear fury. Surrounding it, the convective envelope fills a sphere 764 solar radii wide. The vast majority of Betelgeuse, the part you can see with your eyes from 500 light-years away, is essentially empty. A thin soup of hydrogen and helium, churning in enormous convective cells, loosely held together by the gravity of that tiny core. But which stage is Betelgeuse actually in right now? That question turns out to be one of the most contested in stellar astrophysics, and it matters enormously because the answer determines whether Betelgeuse will explode in 100,000 years or within a human lifetime. The majority view, supported by Wheeler and Chatzopoulos in their comprehensive 2023 review, is that Betelgeuse is currently burning helium in its core. Helium burning is the longest post-main sequence phase, lasting roughly 1 million years for a star of this mass. Statistically, if you pick a random red supergiant and ask what stage it is in, the answer is almost certainly helium burning, simply because that phase lasts so much longer than everything that follows. Carbon burning lasts 1,000 years. Neon burning lasts a year. The chances of catching a star in those brief windows are tiny, but in 2023, a team led by Hideyuki Sayo published a paper that sent shockwaves through the astronomical community. They reinterpreted Betelgeuse's pulsation periods, particularly the mysterious long period of about 2,200 days, as a radial fundamental pulsation mode, rather than the unexplained long secondary period that had puzzled observers for decades. When they matched all 4 of Betelgeuse's known pulsation periods to theoretical models, the best fit pointed to a star in late-stage core carbon burning, with an initial mass of about 19 solar masses and a current mass of about 11 to 12. If correct, and if Betelgeuse was nearing the end of its carbon burning phase, a supernova could happen within tens of years. Not thousands, not hundreds of thousands, tens. The rebuttal came fast. Molnar, Joyce, and Leung pointed out that Sayo's model requires a stellar radius of about 1,400 solar radii, which conflicts with the angular diameter measurements that consistently indicate a radius between 600 and 1,000. In other words, the model works mathematically, but predicts a star significantly larger than what we actually observe. And then came the discovery that may have resolved the debate entirely, but not in the way anyone expected. We need to talk about what happened in July 2025. But before we get there, we need to talk about what happened in late 2019, because that is when Betelgeuse did something it had never done in recorded history, and it scared the entire astronomical world. In October 2019, Betelgeuse started dimming, not the subtle fluctuations it had always been known for, not the gentle brightening and fading of its 420-day pulsation cycle. Something different, something dramatic. Astronomers at Villanova University, Edward Guinan and Richard Wassertonic, along with amateur observer Thomas Calderwood, were the first to raise the alarm. On December 8, 2019, they issued an alert through the Astronomer's Telegram, reporting that Betelgeuse had dropped to a modern all-time low magnitude of plus 1.12, and it was still getting dimmer. Through January 2020, the decline accelerated. Betelgeuse fell below Aldebaran, the bright orange star in Taurus, something that had not happened in living memory. It dropped out of the top 20 brightest stars. People who knew nothing about astronomy started noticing that Orion looked different. One of the most recognizable constellations in the sky had a shoulder that was visibly, undeniably fading. Then, between February 7th and 13th, 2020, Betelgeuse hit bottom. Visual magnitude plus 1.614, plus or minus 0.008, the faintest it had been recorded in nearly 200 years of systematic observation. The star had lost roughly 65% of its visible light. Images from the Very Large Telescope's Sphere instrument showed something haunting. The southern hemisphere of the star had become 10 times darker than normal. It looked like someone had taken a bite out of it. Half the star's face had gone dark. The internet lost its mind. Headlines screamed about imminent supernovae. Social media was flooded with speculation. Is Betelgeuse about to explode? Are we about to witness a supernova? Should we be worried? The excitement was understandable because the dimming was extraordinary, visible to the naked eye, and Betelgeuse was already known to be a star nearing death. The timing felt almost too perfect. But Betelgeuse was not exploding. What was happening was, in many ways, more scientifically interesting than a supernova, because the Great Dimming, as it came to be called, revealed a phenomenon that had never been observed on any star before, something that rewrote our understanding of how massive stars lose mass and interact with their environments. The cause turned out to be a perfect storm of two simultaneous processes. The first was a surface mass ejection. In January through March of 2019, months before the visible dimming began, a vigorous convective plume more than 1 million miles across had risen from deep inside the star. This was not unusual in itself. Betelgeuse's surface is dominated by enormous convective cells, vast bubbles of hot plasma rising from the interior like the blobs in a lava lamp. Except each one is comparable in size to Earth's orbit around the Sun. But this particular plume generated a photospheric shock, a pressure wave in the star's visible surface layer that did something unprecedented. It ejected a chunk of the star itself outward into space. Not material from the corona, the way the Sun ejects plasma in coronal mass ejections. Material from the photosphere, the dense visible surface of the star. The distinction matters enormously. Solar CMEs are eruptions from the Sun's thin, hot outer atmosphere, This was an eruption from the body of the star. Andrea Dupree, whose team at the Harvard-Smithsonian Center for Astrophysics had been monitoring Betelgeuse with Hubble as part of a 3-year ultraviolet survey, detected the ejected material using Hubble's Space Telescope imaging spectrograph. Magnesium emission lines showed hot plasma racing outward through the chromosphere months before anyone noticed the dimming invisible light. As Dupree put it, with Hubble, we could see the material as it left the star's surface and moved out through the atmosphere before the dust formed that caused the star to appear to dim. The scale of this ejection was almost beyond belief. Dupree's team established that the surface mass ejection blasted off 400 billion times as much mass as a typical solar coronal mass ejection. 400 billion times. The ejected material traveled outward at roughly 200,000 miles per hour, and as it cooled millions of miles from the star, it condensed into silicate dust grains. These dust grains formed a cloud more than 100 million miles wide that parked itself between Betelgeuse and Earth, blocking roughly a quarter of the stellar disk. Dupree noted that nothing like this had ever been observed. We have never before seen a huge mass ejection of the surface of a star, she said. We are left with something going on that we do not completely understand. The second factor was simpler, but equally important. A large convective cell on the photosphere had cooled significantly, independent of the dust cloud. The effective temperature dropped by at least 170 Kelvin, from about 3650 Kelvin to around 3450 to 3500. This might sound like a small change, but stellar luminosity depends on temperature to the fourth power. A modest temperature drop translates to a significant reduction in light output, and the cooling also increased molecular opacities in the atmosphere, further reducing the star's apparent brightness. A 2022 study using data from Japan's Himawari 8 weather satellite, which happened to have Betelgeuse in its field of view, found that the temperature drop and the dust cloud contributed to the dimming in roughly equal measure. The timing was particularly bad, or depending on your perspective, particularly illuminating. The surface mass ejection coincided with the minimum of Betelgeuse's 420-day pulsation cycle, the phase when the star is at its smallest and coolest. This may have amplified the ejection by reducing the escape velocity at the surface. It was a convergence of events, each one capable of causing noticeable dimming on its own, combining to produce the most dramatic change in a naked eye star in modern history. Betelgeuse recovered to approximately normal brightness by April 2020. But the aftermath was not over. Something had changed inside the star, and the evidence was unmistakable. The 400-day fundamental pulsation period, which had been measured consistently for nearly 200 years, was disrupted. The regular breathing cycle that astronomers had tracked since the early 1800s had been knocked off rhythm. A new dominant periodicity of about 200 days, corresponding to the first overtone mode, replaced the fundamental. Morgan McLeod and collaborators described the interior as sort of bouncing, sloshing around like an imbalanced washing machine tub. They predicted the fundamental 400-day mode should return within 5 to 10 years by roughly 2025 to 2030. As of early 2026, the recovery is still in progress. And then, in April 2023, Betelgeuse surprised everyone again. It brightened to magnitude plus 0.0, about 142 to 156% of its normal brightness, the brightest it had been in recent recorded history. Cue another round of headlines. Is Betelgeuse about to explode again? Scientists attributed the extreme brightness to ongoing recovery oscillations, essentially the star overcorrecting after the trauma of the Great Dimming, not pre-supernova behavior. But it underscored something important. Betelgeuse is not a stable object. It is a star in active turmoil, and its behavior over the last several years has been unlike anything we have documented before. The Great Dimming taught us three things. First, massive stars can lose material, not just through steady winds, but through explosive ejections from their photospheres, a mechanism 400 billion times more powerful than anything the Sun produces. Second, the convective interior of a red supergiant is violently unstable, capable of producing surface disturbances that take years to recover from. And third, we are watching all of this happen on a star that is, by any measure, nearing the end of its life. Whether that end comes in 100 years or 100,000, the processes that will ultimately kill Betelgeuse are already visible. The star is losing mass, shaking itself apart, and running out of fuel. The Great Dimming was not a sign that the end was near. It was a window into the mechanics of how that end will eventually arrive. But back to the question that matters most. When? The answer depends on what is happening in a region we cannot see, a region smaller than Earth at the center of a star 3.5 astronomical units wide. If helium is burning in that core, Betelgeuse has roughly 10,000 to 100,000 years remaining. If carbon is burning, we are down to centuries or less. If somehow the core has progressed to neon or beyond, we are talking years. And when the core reaches iron, when that Earth-sized ball of degenerate matter can no longer extract energy from nuclear fusion, the end will come not in years or months, but in seconds. The iron core will collapse at 1/4 of the speed of light. Electron capture will convert protons to neutrons, releasing a flood of neutrinos so intense that for about 10 seconds, the collapsing core will emit more energy in neutrinos alone than the rest of the observable universe emits in light. The outer layers, still unaware that the core has vanished beneath them, will fall inward and slam into the newly formed neutron star, bouncing outward in a shockwave that rips the star apart. When Betelgeuse finally detonates as a Type II core collapse supernova, the show will be spectacular. Simulations by Goldberg and Bauer at UC Santa Barbara predict a peak brightness of roughly -10 to -11 on the apparent magnitude scale. That is comparable to the half moon. For context, the brightest historical supernova ever recorded was SN 1006, which reached magnitude -7.5. Betelgeuse's supernova would be roughly 10 to 40 times brighter than that. It would be clearly visible in full daylight, a brilliant point of light burning in Orion's shoulder that you could see at noon with the sun blazing overhead. Astronomer Andy Howell described what it would look like. This incredibly intense beacon in the sky that would cast shadows at night and that you could see during the daytime. It would remain visible to the naked eye for several years as it slowly faded, potentially 6 to 12 months at its brightest. and after it faded, Orion would be permanently disfigured. The left shoulder, one of the most recognizable features of one of the most recognizable constellations in the sky, would be gone, replaced by a faintly glowing supernova remnant that only telescopes could see. But here is the reassuring part. At 500 to 700 light years, Betelgeuse is 10 to 25 times farther from Earth than the danger zone for a supernova, which is roughly 25 to 50 light years. The inverse square law is your friend here. By the time the radiation reaches us, it has spread out over such an enormous volume of space that it would be far too diluted to cause biological harm. No ozone depletion, no mass extinction, no significant radiation exposure. Just the most spectacular light show in recorded human history. We would even get advance warning. Neutrino observatories, including Super Kamiokande in Japan, IceCube at the South Pole, and the upcoming Dune detector, would detect a flood of millions of neutrinos arriving several hours before the visible light. The Supernova Early Warning System, appropriately abbreviated SNEWS, would alert astronomers worldwide, giving them time to point every telescope on and above Earth at Betelgeuse before the light show began. The neutrinos themselves are completely harmless. Trillions of neutrinos from the Sun pass through your body every second without interacting with a single atom. And supernova neutrinos are no different. There is one more thing people worry about with supernovae: gamma ray bursts, the focused jets of energy that can sterilize entire regions of a galaxy. Betelgeuse will not produce one. Its rotational axis is inclined about 20 degrees to our line of sight, and more importantly, it does not have enough mass. Dangerous gamma ray bursts require progenitors above roughly 25 solar masses, and Betelgeuse falls below that threshold. Any cosmic rays from the explosion would take about 100,000 years to reach Earth, diffused to complete insignificance by interstellar magnetic fields. After the fireworks are over, what will be left? The most likely remnant is a neutron star of approximately 1.5 solar masses, a ball of nuclear matter about 12 miles across, spinning hundreds of times per second, with a surface gravity 200 billion times stronger than Earth's, and a teaspoon of its material weighing 6 billion tons. Betelgeuse does not appear massive enough to form a black hole. That typically requires progenitors above about 25 solar masses. The expanding supernova remnant, a cloud of gas enriched with the elements forged in the star's interior, and the explosion itself, would be visible for tens of thousands of years and would become one of the closest and best studied supernova remnants in astronomical history. But all of this is in the future. Whether that future is 100 years or 100,000 years remains genuinely unknown. And the reason it remains unknown brings us to one of the most fascinating aspects of Betelgeuse. The thing is not just big. It is turbulent, violently active, and in some ways deeply mysterious even after a century of intensive observation. Consider the convective cells. Martin Schwarzschild predicted in 1975 that red supergiant envelopes would host just a small number of enormous convective structures, in dramatic contrast to the Sun's surface, which is covered with millions of tiny granules, each about 1,000 kilometers across. On Betelgeuse, the granules are not tiny. They are monsters. Lopez, Ariste, and collaborators, using spectropolarimetric imaging at Pic du Midi Observatory in 2018, demonstrated that Betelgeuse's convective cells have a characteristic size exceeding 60% of the stellar radius. Each one is comparable in scale to Earth's entire orbit around the Sun. At any given time, the star hosts roughly 2 to 4 dominant convective structures on its visible hemisphere. These are not gentle updrafts, they are violent. Plasma rises at speeds of 22 kilometers per second, which is supersonic within the star. It falls back down at about 10 kilometers per second. And in extreme cases, convective upflows reach 60 kilometers per second, approaching the star's escape velocity. This suggests that convection is not just a process happening inside the star. It is actively throwing material off the star. The surface mass ejection that caused the Great Dimming may have been an extreme example of what the star's convection does routinely on smaller scales. Individual convective structures can be tracked for years, though changes occur on timescales as short as 1 week. ALMA detected a hotspot about 20 milliarcseconds across with a temperature excess of roughly 1,000 Kelvin above the surrounding surface, large enough to physically distort the shape of the stellar limb. Betelgeuse's convective cells are not like bubbles in boiling water. They are more like continents of rising plasma, each one covering a significant fraction of the star's surface, each one hot enough and violent enough to reshape the star itself. This connects to one of Betelgeuse's most persistent puzzles. It is spinning far too fast. ALMA observations revealed what appears to be surface rotation of about 5 to 6.5 kilometers per second. That does not sound fast until you consider that conservation of angular momentum during the massive expansion from main sequence to supergiant should have slowed the rotation to about 0.1 kilometers per second. A star that expanded from a compact blue furnace to a sphere 3.5 astronomical units wide should be spinning almost imperceptibly slowly. Instead, it is rotating roughly 50 to 65 times faster than physics predicts. 3 explanations have been proposed. The first is that Betelgeuse swallowed a companion star at some point in the past. Chatsopoulos and collaborators modeled this in 2020, and Scheiber and collaborators refined the simulations in 2024. A merger between a 16 solar mass primary and a 1 to 4 solar mass secondary occurring hundreds of thousands of years ago could transfer enough angular momentum to explain the observed rotation. The simulations also predicted nitrogen enrichment, matching what we observe, and a high space velocity consistent with Betelgeuse's measured motion of about 30 kilometers per second through the interstellar medium. The second explanation involves the newly discovered companion star, which we have not talked about yet, and which changes the story considerably. The third explanation is potentially the most elegant. Ma and collaborators demonstrated in 2024 that the large-scale convective motions on Betelgeuse's surface can mimic rotation in spectroscopic data. When you observe a star with a few enormous convective cells, some rising toward you and some falling away, the velocity field can look exactly like rotation, even if the star is barely spinning at all. Their analysis suggested a 90% probability of false detection at rotation speeds of 2 kilometers per second or above. In other words, the rotation we think we see might not be rotation at all. It might just be the convective cells fooling us. And this is what makes Betelgeuse such a remarkable object to study. Even the most basic questions, how big is it? How fast is it spinning? What fuel is it burning? Are still genuinely contested. This is a star close enough and bright enough that we have been staring at it with every instrument we have for over a century. And it still surprises us. The great dimming surprised us. The recovery surprised us. The extreme brightening in 2023 surprised us. And the discovery that happened in 2025 surprised everybody. Because it turns out that Betelgeuse is not alone. It has a companion, and the existence of that companion may resolve one of the longest-running mysteries in stellar astrophysics. But it also raises a possibility that nobody anticipated. The companion might fall in. And if it does, it might do so before the supernova even happens. But to understand what that means and why it sent shockwaves through the astronomical community, you need to understand the full picture of what Betelgeuse is doing to the space around it. Because this star is not just passively sitting there, it is actively destroying its own neighborhood. Betelgeuse sheds material at roughly 1/1,000,000th of a solar mass per year. That sounds small, but it means the star is losing the equivalent of one entire sun's worth of material every million years. Since leaving the main sequence, it has shed an estimated 5 to 9 solar masses of material, meaning the Betelgeuse we see today is significantly lighter than the Betelgeuse that was born. All that lost mass has not disappeared. It has formed an enormous asymmetric circumstellar envelope stretching roughly 250 times the star's radius. Astronomers have identified at least 6 distinct shells of material surrounding the star, like tree rings, recording different episodes of mass loss over hundreds of thousands of years. The inner gaseous envelope extends to about 2 to 3 stellar radii from the photosphere. This is where you find warm, relatively dense gas being actively fed by the stellar wind and convective ejections. Further out, at about 1.5 to 3 stellar radii, temperatures drop to around 1300 Kelvin. That is cool enough for dust to condense. Silicate grains form here, the same kind of dust that blocked Betelgeuse's light during the Great Dimming. Hubble's imaging spectrograph has detected warm plasma extending to at least 200 astronomical units from the star. And the largest shed shells, the outermost whispers of material that Betelgeuse has thrown off over its lifetime, reach nearly 7.5 light years from the star. 7.5 light years of expelled stellar material, trailing behind and around a single star like an enormous ghostly wake. And then there is the bow shock. Betelgeuse is not stationary relative to the interstellar medium. It barrels through the thin gas between the stars at roughly 30 kilometers per second, about 67,000 miles per hour. At that speed, the stellar wind and the shed material pile up in front of the star like water in front of a boat's hull, creating a bow shock. The ESA's Herschel Space Observatory imaged this structure in far infrared light, and the result was stunning. The bow shock spans over 4 light years across, consisting of broken, dusty arcs at 6 to 7 arc minutes from the star, with dust temperatures between 40 and 140 Kelvin. Beyond the bow shock, at about 9 arc minutes, there is a mysterious linear structure, a kind of bar or wall that astronomers believe is probably the edge of an interstellar cloud rather than material from Betelgeuse itself. At the star's current velocity, the outermost bull shock arc will collide with this bar in about 5,000 years. The star itself will reach it in about 12,500 years. Though the gas is too thin for any destructive interaction, it will be a spectacular collision to observe if anyone is still around to observe it. The bow shock tells us something important about Betelgeuse's biography. A star moving that fast through the interstellar medium has a story. 30 kilometers per second is unusually quick for a red supergiant. One explanation is that Betelgeuse was ejected from a star-forming region, perhaps by a gravitational interaction with other massive stars. Another is that a past merger event, the same one that might explain the anomalous rotation, gave the system a velocity kick. Whatever the cause, Betelgeuse is plowing through space fast enough to leave a trail that stretches across light years, a cosmic contrail marking the path of a dying star. Let us step back in time for a moment, because one of the most remarkable things about Betelgeuse is how long humanity has been watching it, and how what we have seen has changed over the centuries. The oldest known observations of Betelgeuse's variability do not come from European astronomers or Chinese court records. They come from Aboriginal Australian oral traditions, and they may be the oldest astronomical observations in any culture on Earth. Dwayne Hamaker at Macquarie University documented in 2018 how stories from the Great Victoria Desert of South Australia describe the star Nyaruna, which is associated with Orion and identified with Betelgeuse, as a figure that fills with fire magic and then dissipates. This directly encodes knowledge of the star's brightness changes. Bradley Schaefer independently confirmed that the Aboriginal Australians could and did discover the variability of Betelgeuse. These oral traditions potentially span 65,000 years or more, making them far older than any written astronomical record from any civilization. For perspective, the earliest Sumerian astronomical records are roughly 5,000 years old. The Aboriginal observations may predate them by a factor of 13. But the most tantalizing historical question about Betelgeuse is not whether ancient people noticed its brightness changes. It is whether they noticed its color. Because there is compelling evidence that Betelgeuse has changed color within recorded history, and the implications are extraordinary. Around 137 AD, the Greek-Egyptian astronomer Ptolemy compiled his Almagest, the most influential astronomical text of the ancient world. In it, he described Betelgeuse using the Greek term hypokeiros, which means pale yellow or tawny. More importantly, he did not include Betelgeuse in his list of distinctly red stars, a list that featured Antares, Aldebaran, and Arcturus. If Betelgeuse had been the deep orange red we see today, Ptolemy would almost certainly have included it alongside those other red stars. He did not. Chinese astronomical records from roughly 300 years before Ptolemy also appear to describe a yellow-colored Betelgeuse. By the 16th century, Tycho Brahe noted the star was more red than Aldebaran. A landmark 2022 study by Neuhauser and collaborators synthesized 2,000 years of records from Greek, Roman, Chinese, and other sources to conclude that Betelgeuse changed from yellow-orange to red within approximately 2 millennia. This is consistent with the star crossing, what astronomers call the Hertzsprung gap, the transition region on the Hertzsprung-Russell diagram between the blue main sequence and the red supergiant branch. In other words, humanity may have been watching Betelgeuse evolve in real time, watching it transform from a relatively hot yellow star to the cool red giant we see today. 2,000 years is an eye blink in stellar evolution, but it is exactly the timescale you would expect for a massive star making the final transition to the red supergiant phase. Even the star's name carries a trace of history's confusion. Betelgeuse derives from the Arabic Yad al-Jawza, meaning the hand of Orion. During medieval Latin transliteration, scribes misread the initial Arabic letter Ya as Baye. Those two letters in Arabic script differ by only a single dot, one placed above and one below an identical shape. The tiny scribal error transformed Yad into Bad, which eventually became Betelgeuse. Renaissance scholars, working with the corrupted spelling, tried to make sense of it by connecting it to the Arabic word IBT, meaning armpit. This produced the popular but incorrect etymology, the armpit of the central one. The correct translation is the hand. A single misplaced dot, roughly 800 years ago, is why we call the star what we call it today. The pronunciation, for what it is worth, has never been settled either. Betelgeuse, Betelgeuse, and several other variations all have their defenders, and the arguments about which is correct have outlasted most of the arguments about the star's actual physical properties. The first time anyone measured the physical size of Betelgeuse was December 13th, 1920. Albert Michelson and Francis Pease mounted a 20-foot stellar interferometer on the 100-inch Hooker telescope at Mount Wilson Observatory in California and measured Betelgeuse's angular diameter at 0.047 arcseconds, 47 milliarcseconds. This was a landmark achievement. It was the first time anyone had ever measured the angular diameter of any star other than the Sun. Every star before that had been a point of light, indistinguishable from a mathematical dot. Betelgeuse was the first star to have a measurable width. Michelson and Pease calculated a physical diameter of about 240 million miles, roughly matching the orbit of Mars. Published in the May 1921 Astrophysical Journal, their result confirmed a theoretical prediction by Arthur Eddington, and it opened the door to the modern era of stellar astrophysics, where stars became physical objects with measurable sizes rather than mere points of light. Modern telescopes have taken that door and blown it off its hinges in 1995 and 1996. Andrea Dupre and Ronald Gilliland used Hubble's faint object camera to produce the first direct image of the surface of any star other than the Sun. The image showed Betelgeuse's ultraviolet atmosphere, asymmetric and lopsided, with a mysterious hotspot in the southwestern quadrant that was at least 2,000 Kelvin hotter than the surrounding surface. Nobody knew what the hotspot was. Some suggested it was a rotational pole. Others thought it might be a convective upwelling. The debate continued for years. In 2009, the Very Large Telescope's adaptive optics system revealed a bright plume extending at least 6 stellar radii from Betelgeuse, roughly 30 astronomical units, a stream of material reaching further from the star than Neptune orbits from our Sun. ALMA produced the first sub-millimeter image of any stellar surface in 2017, revealing the temperature structure of the photosphere and detecting the hotspot that would later be shown to physically distort the shape of the stellar limb. The VLT's SPHERE instrument captured the dramatic before and after images of the Great Dimming in 2020, showing the stark difference between a healthy Betelgeuse and a wounded one. And in 2022, Lopez Ariste and collaborators produced the first three-dimensional images of convective cells on any star using spectropolarimetry, finally confirming Schwarzschild's 1975 prediction that red supergiants would have just a handful of enormous convective structures rather than millions of tiny ones. A century of progressively sharper images has revealed Betelgeuse to be emphatically not spherical. Interferometric imaging since the late 1980s has shown bright hotspots, asymmetric brightness distributions, and time-varying shape changes. The star's apparent shape shifts continuously as convective cells evolve, brightening and darkening different regions of the surface on timescales of weeks to months. It is not a tidy sphere. It is a lumpy, boiling, pulsating blob of almost nothing, held loosely together by the gravity of a tiny core, surrounded by shells of its own shed material, plowing through interstellar space at 67,000 miles per hour and slowly, inexorably running out of fuel. And it was this star, this magnificently chaotic, endlessly surprising object, that turned out to have a secret companion orbiting just beyond its surface. The discovery happened in stages, and it started with a mysterious period. For decades, Betelgeuse had been known to vary in brightness with at least 4 distinct periods. The primary period, about 420 days, represents the star's fundamental radial pulsation, the whole star expanding and contracting like a beating heart. A secondary period of about 230 days and a tertiary of about 185 days correspond to higher overtone modes, faster oscillations superimposed on the fundamental pulse. But the fourth period, the longest one at roughly 2200 days, about 6 years, was strange. It did not fit neatly into any pulsation model. It was classified as a long secondary period, which in stellar astrophysics is essentially code, for we see this periodicity, but we do not know what causes it. Long secondary periods are observed in many red giants and supergiants, and despite decades of study, their physical origin remained one of the unsolved problems in variable star research. Several explanations had been proposed. Convective turnover, the time it takes for a convective cell to rise and sink, could produce long-term brightness variations. Strange mode pulsations, exotic oscillation modes unique to very luminous stars, were another possibility. Magnetic cycles, analogous to the Sun's 11-year activity cycle, but scaled up to supergiant proportions, had been suggested. None of these explanations fully matched the observations. Then, in 2024, Jared Goldberg, Meredith Joyce, and Laszlo Molnar published a paper with a provocatively simple title, A Buddy for Betelgeuse. Their argument was systematic and devastating. They went through every proposed explanation for the long secondary period and showed why each one failed. Convection could not produce the observed regularity. Strange modes required unrealistic stellar parameters. Gravity modes were damped too quickly. Magnetic cycles lacked a plausible mechanism. Rotation produced the wrong kind of variability. After ruling out everything internal to the star, one explanation remained: binary orbit. The 2200-day period was not a pulsation. It was the orbital period of a companion star circling Betelgeuse every 5.94 years at a separation of about 1,850 solar radii, roughly 2.4 times Betelgeuse's own radius. They predicted a companion mass of about 1.17 solar masses, give or take 0.7. The astronomical community was skeptical but intrigued. Predicting a companion is one thing, finding it is another. Betelgeuse is so bright that any companion would need to be extraordinarily close in angular terms and enormously fainter, hidden in the glare of one of the brightest stars in the sky. It was like trying to spot a firefly next to a searchlight. But on July 21st, 2025, Steve Howell at NASA's Ames Research Center announced that they had done exactly that. Using speckle imaging with the Alapeak instrument on the Gemini North Telescope in Hawaii, Howell's team detected a faint companion star at an angular separation of 52 milliarc seconds from Betelgeuse. 52 milliarc seconds. That is roughly the apparent width of a dime viewed from 40 kilometers away. The detection, published in the Astrophysical Journal Letters, was consistent with the predictions from the Buddy for Betelgeuse paper. The companion existed, it was real, and it was exactly where the orbital model said it should be. The companion turned out to be a small star, estimated at 1.4 to 2.0 solar masses, most likely about 1.6, roughly 6 magnitudes fainter than Betelgeuse, which means the supergiant outshines it by a factor of about 250. In spectral type, it appears to be a young F-type pre-main sequence star, meaning it has not yet fully settled onto the main sequence. It orbits at approximately 4 astronomical units from Betelgeuse, just beyond the supergiant's optical surface, completing one orbit every 2,170 days, which is 5.94 years. On September 22nd, 2025, the International Astronomical Union's Working Group on Star Names officially named the companion Siwarha, an Arabic word meaning her bracelet. Astronomers, being astronomers, immediately started calling it Beetle Buddy instead. Both names stuck. But the discovery was not just a fun addition to the Betelgeuse story. It had immediate and far-reaching consequences for how we understand the star. The most significant was that it provided a natural explanation for the 2,200-day long secondary period. That mysterious signal was not a pulsation of Betelgeuse at all. It was the orbital motion of Siwarha, tugging gravitationally on the supergiant and modulating its brightness as the companion moved closer and farther on its elliptical path. This reattribution had a cascading effect through the literature. Remember the 2023 paper by Sayo and collaborators, the one that claimed Betelgeuse was in late-stage carbon burning and might explode within tens of years? That paper's entire argument depended on interpreting the 2,200-day period as a radial fundamental pulsation mode. If the 2,200-day signal is not a pulsation but an orbit, the foundation of their analysis collapses. The periods no longer match a carbon-burning model. The imminent supernova hypothesis, already challenged on other grounds, lost its most important piece of evidence. Then, in January 2026, at the 247th meeting of the American Astronomical Society in Phoenix, Andrea Dupree presented another discovery. Using 8 years of Hubble data, her team had detected a dense wake of gas created as Siwarha plows through Betelgeuse's extended atmosphere. Picture this: Betelgeuse's outer atmosphere does not end at the photosphere. It extends far beyond, a thin haze of gas and dust. Siwaha orbits through this material, and as it does, it carves a wake, like a boat moving through fog. Dupree's team found this wake appearing every 6 years or so, exactly when the companion crosses in front of the supergiant as seen from Earth. 8 years of Hubble observations had captured the wake forming, dissipating, and forming again, an independent confirmation of the companion's existence and orbit. And then came the speculation that nobody expected. Morgan McLeod, who had studied the Great Dimming and its aftermath, suggested that Siwaha is not in a stable orbit. It is being drawn closer by gravitational forces, losing energy through interactions with Betelgeuse's extended atmosphere. McLeod estimated that the companion could merge with Betelgeuse within roughly 9,000 years, possibly before the supernova. We think the stars might merge even before Betelgeuse goes supernova, McLeod stated. This would splash out some gas, spin up Betelgeuse, and potentially affect the properties of the eventual supernova. Think about what that means. Betelgeuse, already the most dramatic star in our sky, may be on a collision course with its own companion, a star being slowly consumed by the star it orbits. And the merger, if it happens, would not be quiet. It would eject material, possibly producing a luminous red nova visible to the naked eye. It would transfer angular momentum, spinning up the supergiant, and it would alter the conditions inside Betelgeuse in ways that could change when and how the supernova ultimately occurs. But there is another layer to this story, because the merger with Siwaha might not be the first time Betelgeuse has consumed a companion. Separate from the current binary discovery, there is evidence that Betelgeuse has done this before. In 2020, Emmanuel Chetsopoulous and collaborators proposed that Betelgeuse's anomalously fast rotation could be explained by a stellar merger that occurred hundreds of thousands of years ago. The scenario goes like this. Betelgeuse was originally part of a binary system with a smaller companion, somewhere between 1 and 4 solar masses. As Betelgeuse expanded into a red supergiant, its outer layers engulfed the companion. The smaller star spiraled inward through the supergiant's envelope, transferring its orbital angular momentum to the surrounding gas before being destroyed and absorbed. This process, called common envelope evolution, is violent and messy. It would have ejected a significant amount of material from the system and left the merged star spinning far faster than it should be. In 2024, Ursula Scheiber and collaborators refined these simulations with higher resolution models and found that the merger scenario predicted not just fast rotation, but also nitrogen enrichment on the surface, which matches what spectroscopic observations actually show. Their simulations demonstrated that the merger product would maintain rapid surface rotation for hundreds of thousands of years after the event, long enough for us to still detect it today. The models also produced a velocity kick to the merged system, consistent with Betelgeuse's unusually high space velocity of 30 kilometers per second. So here is the picture that is emerging. Betelgeuse may have already consumed one companion star in its past, an event that spun it up, enriched its surface with nitrogen, and possibly accelerated it through space. Now it has a second companion, Siwaha, that appears to be slowly spiraling inward toward the same fate. If If this interpretation is correct, Betelgeuse is a serial stellar cannibal. It has eaten before, and it may eat again, and the next meal could arrive before the star even has a chance to explode. This raises an obvious question. Is this kind of behavior unusual? Are most red supergiants secretly binary systems, or is Betelgeuse special? The honest answer is that we do not know. Massive stars are overwhelmingly born in binary or multiple systems. Some estimates suggest that over 70% of O-type stars, the kind Betelgeuse started as, have at least one gravitationally bound companion. By the time they evolve to the red supergiant phase, many of those companions will have interacted with the expanding star. Common envelope events, mergers, mass transfers, and orbital disruptions are probably routine. But because red supergiants are so bright, so extended, and so variable, detecting companions around them is extraordinarily difficult. Siwaha was only found because a specific prediction told observers exactly where and when to look. There could be companions around dozens of other red supergiants that we simply have not identified yet. Which brings us to the other red supergiants and the question of where Betelgeuse stands in the hierarchy of stellar enormity. Because as absurd as Betelgeuse's size is, it is not even close to the biggest star we know of. And the story of how we measure these monsters and how spectacularly wrong those measurements can be is itself a cautionary tale about the limits of human knowledge. Betelgeuse's closest analogue in the sky is Antares, Alpha Scorpii, the red heart of the scorpion. The two stars are remarkably similar. Antares has a radius of about 680 solar radii, a mass of 11 to 14 solar masses, a luminosity between 60,000 and 90,000 times the Sun, and sits at roughly 554 light-years from Earth. It is the only other first magnitude red supergiant visible from Earth. In many ways, Antares is Betelgeuse's twin, a star at a similar evolutionary stage, similar mass, similar distance, and similar luminosity. The two even share a rivalry that goes back to antiquity. The name Antares comes from the Greek anti-Ares, meaning rival of Mars, because its red color was easily confused with the planet Mars when they appeared near each other in the sky. Betelgeuse, in Orion, dominates the winter sky. Antares, in Scorpius, dominates the summer. They are never visible at the same time, two dying giants taking turns presiding over the night. But both of them are modest compared to the true Leviathans. Mu Cepae, sometimes called Herschel's garnet star because of its deep red color, has an estimated radius between 972 and 1260 solar radii. If you placed Mu Cepae where the Sun is, its surface would extend well past Jupiter's orbit and approach Saturn's. It is one of the largest stars visible to the naked eye. VY Canis Majoris is bigger still. Classified as a red hypergiant, a category even more extreme than supergiant, VY Canis Majoris has an estimated radius of about 1420 solar radii, roughly 1.9 times Betelgeuse's radius. Its surface, if centered on the Sun, would extend past Jupiter's orbit at 5.2 astronomical units and reach about 6.6 astronomical units, putting it more than halfway to Saturn. VY Canis Majoris is also one of the most luminous stars known, shining at roughly 300,000 times the Sun's luminosity. It is surrounded by a complex nebula of ejected material that has been imaged in stunning detail by Hubble and ALMA, and it is losing mass at a rate roughly 100 times faster than Betelgeuse. And then there is the current record holder, or at least the current claimant, Stephenson 218, a red supergiant in the Stephenson 2 cluster near the center of the Milky Way, has a claimed radius of about 2,150 solar radii. If that measurement is accurate, its diameter would span roughly 20 astronomical units, and its surface would extend past Saturn's orbit at 9.54 astronomical units. It would be so large that light would take roughly 3 hours to travel across it. But many astronomers consider this value unreliable. The star is extremely distant, somewhere around 20,000 light years, making precise measurements extremely difficult. Its claimed radius exceeds what most theoretical models predict is possible for a stable red supergiant. Some researchers suspect the measurement is inflated by the same kinds of systematic errors that plague all giant star measurements, errors that become worse with increasing distance. Which brings us to UY Scuti, and possibly the best cautionary tale in all of stellar astrophysics. UY Scuti was originally measured at 1,708 solar radii, a value that was trumpeted across popular science as the largest known star. YouTube videos with tens of millions of views compared its size to the Sun, to Jupiter, to the entire solar system. It became the poster child for stellar enormity, featured in countless infographics and size comparison animations. There was just one problem. The measurement was wrong. When the Gaia satellite's second data release provided improved distance measurements for millions of stars, the revised distance to UY Scuti shrank its estimated radius to somewhere between 755 and 909 solar radii. That is potentially comparable to, or even smaller than, Betelgeuse, the star that had been advertised to hundreds of millions of people as the biggest known star, might be roughly the same size as a star you can see with your naked eye in the winter sky. Many popular science sources still cite the outdated value. The correction, as corrections often do, traveled much more slowly than the original claim. And this gets to something important about measuring any of these stars. The numbers are not as solid as they look. Defining the surface of a red supergiant is fundamentally ambiguous. The standard definition used by astronomers is the Rosalind radius, the depth at which the optical depth equals 2/3, meaning the point from which photons have a reasonable chance of escaping into space without being absorbed. But even this definition is wavelength dependent. The star appears significantly larger at longer wavelengths because cooler extended atmospheric layers emit more infrared and radio emission. Observe Betelgeuse in visible light and you get one size. Observe it at millimeter wavelengths with ALMA and you get a star nearly twice as wide. Neither measurement is wrong exactly. They are just measuring different things. Distance uncertainties compound the problem enormously. For Betelgeuse, a distance range of 400 to 700 light years produces radius estimates that vary by nearly a factor of 2. For stars tens of thousands of light years away, like Stephenson 218, the uncertainties are even larger. The stars also physically change size through pulsation. Betelgeuse's diameter may vary by as much as 60% over its pulsation cycle. So the question, how big is Betelgeuse, does not have a single answer. It has a range of answers. Depending on when you look, what wavelength you use, how far away you think it is, and what you define as the boundary between star and space. Despite all this uncertainty, there is a real hierarchy. Betelgeuse, at about 764 solar radii, is not among the absolute largest known stars, but it is by far the best studied and the closest. No other red supergiant has been imaged in as much detail or monitored for as long. It is the star that taught us what a red supergiant looks like up close, the one that showed us surface mass ejections, the one that confirmed giant convective cells, the one that revealed how stars shed their mass before dying. If VY Canis, Majoris, or Stevenson 218 are larger, they are also much farther away and much harder to study. Betelgeuse is our window into the final stages of massive stellar evolution, and that makes it more scientifically valuable than any star that merely happens to be wider. And here is something that often gets lost in the size comparisons. The reason Betelgeuse matters is not really about how big it is. It is about what is happening inside it. Because right now, whether it is burning helium or carbon or something even heavier, Betelgeuse is building elements. Every second, nuclear reactions in its core and burning shells are forging atoms that did not exist before. Carbon, oxygen, neon, magnesium, silicon, possibly even iron. These elements are not just academic curiosities. They are the raw materials of planets, of oceans, of organic chemistry, of life. Every carbon atom in your body was forged inside a star through the triple alpha process. The same reaction happening in Betelgeuse's core or its burning shells right now. Every oxygen atom you breathe was built by alpha capture on carbon-12, a reaction occurring in the nuclear furnaces of stars exactly like this one. The calcium in your bones, the iron in your blood, the silicon in the rocks beneath your feet, all of it was manufactured in the onion layer cores of massive stars and scattered into space when those stars exploded. Betelgeuse is a factory for the ingredients of existence, and the supernova that will eventually destroy it will be the delivery mechanism. When a star this massive explodes, the shockwave does not just scatter the elements the core has been building over millions of years. The explosion itself creates new elements through a process called explosive nucleosynthesis. The temperatures and pressures generated by the collapsing core and the rebounding shockwave drive nuclear reactions that would be impossible under normal stellar conditions. Elements heavier than iron, things like gold, platinum, uranium, are primarily created in these extreme events. The expanding supernova remnant will seed the surrounding interstellar medium with enriched material that will eventually collapse into new molecular clouds, form new stars, and build new planets. Our own solar system formed from a molecular cloud that had been enriched by multiple generations of supernovae over billions of years. The iron core of the Earth, the water in the oceans, the oxygen in the atmosphere, all of it passed through the interior of at least one massive star before it ended up here. When Betelgeuse explodes, it will contribute its manufactured elements to the next generation of star and planet formation in this part of the galaxy. 500 years from now, or 500,000 years from now, the atoms that are currently swirling inside that near vacuum sphere 3.5 astronomical units wide will be part of something else entirely. Maybe a rocky planet, maybe an ocean, maybe eventually a living thing that will look up at the sky and wonder where its atoms came from. This is what makes Betelgeuse more than a spectacle. It is a participant in the cycle that produces everything we know. Massive stars are the universe's element factories, and supernovae are the distribution network. Without stars like Betelgeuse, living fast, burning hot, and dying violently, the universe would contain nothing heavier than lithium. No carbon, no oxygen, no silicon, no iron, no planets, no chemistry, no biology. The scale of Betelgeuse is not just an interesting fact about one particular star. It is a direct consequence of the nuclear physics that makes complex matter possible. There is one more comparison worth making, and it is the one that sits right next to Betelgeuse in the sky. Rigel, Beta Orionis, the bright blue-white star at Orion's opposite foot. Rigel is actually slightly more massive than Betelgeuse, at about 21 solar masses. But its radius is only 74 to 79 solar radii, roughly 1/10 of Betelgeuse's. As a blue supergiant with a surface temperature of about 12,100 Kelvin, Rigel represents a completely different evolutionary phase. It may eventually expand into a red supergiant similar to Betelgeuse, or it may have already passed through a red supergiant phase and loop back to the blue side of the Hertzsprung-Russell diagram. Some massive stars do this, bouncing between blue and red supergiant phases as their internal structure evolves. The contrast between Betelgeuse and Rigel, two stars of similar mass in the same constellation, one bloated and red and dying, the other compact and blue and furiously hot, illustrates the extraordinary diversity of outcomes possible for massive stars. Red supergiants as a class occupy luminosity class 1 on the stellar classification system and arise from stars of roughly 9 to 40 solar masses. Red hypergiants, sometimes designated as luminosity class 1A0 or 1A+, represent the extreme upper end. They are characterized by enormous luminosity, extreme mass loss, and extended atmospheres that blur the boundary between star and circumstellar environment. The dividing line between supergiant and hypergiant is defined by the Humphreys-Davidson limit, an empirical upper luminosity boundary at roughly 500,000 times the Sun's luminosity for cool stars. Stars above about 40 solar masses cannot become red supergiants at all. They are simply too luminous. The radiation pressure from their cores would blow apart a cool extended envelope before it could stabilize. These most massive stars stay hot, evolving as blue supergiants or Wolf-Rayet stars, shedding mass through ferocious winds until they eventually explode. Betelgeuse, at about 87,000 times the Sun's luminosity, sits well below the Humphreys-Davidson limit as an intermediate luminosity supergiant. But as the Great Dimming showed, it exhibits some hypergiant-like behavior, including surface mass ejections and a complex circumstellar structure that would not be out of place around a much more extreme star. So where does all of this leave us in early 2026? What do we actually know about Betelgeuse, and what remains genuinely uncertain? We know its approximate size: 764 solar radii, give or take enough uncertainty to keep the argument going for another decade. We know its approximate mass: 16 to 19 solar masses, though the SIO models that predict a lower mass of 11 to 12 have not been definitively ruled out. We know its approximate distance: 548 light-years, with a range wide enough to make any physicist uncomfortable. We know it is losing mass, shedding itself into space at a rate that has already stripped away a significant fraction of its birth weight. We know its surface is dominated by a handful of enormous convective cells that are violent enough to throw material into space and chaotic enough to reshape the star's appearance on timescales of weeks. We know it has a companion star, Sawara, that orbits every 6 years and may be spiraling inward toward an eventual merger. We know it has probably already consumed a companion star in the past, an event that may explain its fast rotation and high velocity. We know the great dimming of 2019 through 2020 was caused by a surface mass ejection and photospheric cooling, not by pre-supernova behavior. And we know that when it eventually explodes, the supernova will be the most spectacular celestial event in recorded human history, visible in daylight for months and casting shadows at midnight. What we do not know is when, and the reason we do not know, the reason we may never know until the neutrinos actually arrive at our detectors, is that the information we need is locked inside a region we cannot observe. The core of Betelgeuse, where the nuclear burning that determines the star's fate is happening, is hidden behind 3.5 astronomical units of convective envelope. No photon from the core reaches us directly. No electromagnetic signal of any kind can tell us whether helium or carbon or something heavier is currently fusing at the center. The surface of the star would look virtually identical, whether it has 100,000 years left or 100. The exterior of a red supergiant is the universe's greatest poker face. The SciO claim that Betelgeuse is burning carbon and could explode within decades has been significantly weakened by the discovery of Sawara, which reattributes the key pulsation period to orbital motion rather than internal physics. But significantly weakened is not the same as disproven. And even the consensus estimate of 10,000 to 100,000 years is just that, an estimate based on statistical arguments about which evolutionary phase is most likely given the star's observable properties. Nobody is measuring the core directly. Nobody can. This is worth dwelling on for a moment because it represents one of the most profound limitations in all of observational astronomy. We can image the surface of Betelgeuse in multiple wavelengths. We can track its convective cells. We can measure its pulsation periods to exquisite precision. We can detect the chemical composition of its atmosphere and stellar wind. We can see the bow shock it creates as it moves through space and the shells of material it has shed over hundreds of thousands of years. We can even detect the gravitational influence and direct light of a companion star orbiting at its doorstep. But we cannot see the thing that actually matters. The tiny Earth-sized core where the countdown clock is running. Every external measurement we make is, in some sense, an attempt to infer what is happening in a region the size of a planet by observing the behavior of a gas sphere hundreds of millions of kilometers across. It is like trying to diagnose a heart condition by studying how the patient's hair grows. There is a 2024 study by Pilot and collaborators that adds another layer of uncertainty. Using 10 years of spectropolarimetric data, they argued that at least some of Betelgeuse's shorter pulsation periods may be driven not by classical radial pulsation, but by surface convection. The giant convective cells, rising and falling with their own semi-regular rhythms, could be mimicking periodic behavior in the photometric data. If true, this means some of the fundamental measurements used to constrain Betelgeuse's evolutionary state may be contaminated by surface effects that have nothing to do with the core. The star may be even more opaque to our understanding than we thought. The James Webb Space Telescope has been turned toward Betelgeuse for infrared observations of the circumstellar environment, probing the dust and gas that surround the star in wavelengths that were previously inaccessible at this resolution. The Very Large Telescope Interferometer's Matisse instrument has produced new mid-infrared interferometric images that constrain dust formation models. ALMA continues to monitor the surface at sub-millimeter wavelengths, tracking the evolution of convective cells and hotspots over timescales of months and years. Every major observatory in the world has Betelgeuse on its observation list, and the data are accumulating faster than theorists can process them. But all of this data is surface data, atmospheric data, circumstellar data. None of it penetrates to the core. The only signal that could definitively tell us the core has finally collapsed would be neutrinos. When the iron core gives way and the inner regions implode at a quarter of the speed of light, the collapsing matter will release a burst of roughly 10 to the 58th power neutrinos in approximately 10 seconds. These ghost particles, barely interacting with matter, would stream outward from the core at nearly the speed of light, passing through the entire star in seconds, as if it were not there. They would arrive at Earth several hours before the light of the explosion, because the visible supernova signal is delayed by the time it takes the shockwave to propagate through the stellar envelope and reach the surface. When those neutrinos arrive, the supernova early warning system will trigger. Super Kamiokande in Japan, a tank filled with 50,000 tons of ultra-pure water buried a kilometer underground, will detect several thousand neutrino interactions in a burst lasting about 10 seconds. Ice Cube at the South Pole, a cubic kilometer of Antarctic ice instrumented with thousands of optical sensors, will see a sudden spike in its background count rate. June, the deep underground neutrino experiment being built in South Dakota, will capture the electron-neutrino component with unprecedented precision. Within minutes, automated alerts will go out to every observatory on the planet and in orbit. Astronomers will have a few hours of advance warning to point their telescopes at Orion before the light arrives. That moment, if it comes in our lifetimes, will be the most coordinated observation in the history of science. Every telescope, every detector, every satellite with the capability to observe will be focused on a single point in the sky. The data collected in those first hours and days will reshape our understanding of core collapse physics, neutron star formation, nucleosynthesis, neutrino physics, and stellar evolution. It will answer questions that have been debated since the 1930s. It will be, by any reasonable measure, one of the most important scientific events in human history. But it probably will not happen in our lifetimes. Almost certainly not. The statistical argument is overwhelmingly in favor of helium burning, which gives us tens of thousands of years. The carbon burning hypothesis has been weakened, not destroyed, but weakened significantly enough that most astronomers place their confidence in the longer timescale. We are probably not the generation that gets to see it, and yet Despite all this uncertainty, despite the contested measurements and the debated models and the star that refuses to sit still long enough to be properly characterized, Betelgeuse remains the single most valuable natural laboratory we have for understanding how massive stars die. It is close enough to image directly, bright enough to study with virtually every instrument in existence, variable enough to generate new data constantly, and dramatic enough to keep the entire astronomical community paying attention. No other star combines all of these properties. The picture that emerges after a century of observation and the last few extraordinary years of discovery is of a star in genuine turmoil. It pulsates, it churns, it sheds mass. It traumatically ejects chunks of its own photosphere. It is gravitationally entangled, with a companion spiraling slowly inward. It may have already consumed a previous companion. Its convective surface roils with a handful of enormous cells, each one the size of Earth's orbit, rising at supersonic speeds and occasionally approaching escape velocity. Its shape changes on timescales of weeks. Its brightness has behaved erratically since the Great Dimming, overshooting normal by 50%, disrupting pulsation rhythms that have been stable for 2 centuries. Everything about this star screams instability. Everything about it screams ending. But not yet. Almost certainly not yet. On cosmic timescales, astonishingly soon. On human timescales, almost certainly not in our lifetimes, though you can never be fully certain when you are dealing with a star whose interior is invisible and whose behavior keeps surprising the people who study it most closely. There is something profound about Betelgeuse that goes beyond the measurements and the models. It is the most visible reminder in our night sky that stars die. Most of the stars you see when you look up on a clear night are stable, middle-aged things, fusing hydrogen quietly and reliably for billions of years. They will not change perceptibly in your lifetime, or your children's lifetimes, or your civilization's lifetime. They are the furniture of the sky, steady and dependable, and utterly boring from a dramatic standpoint. Betelgeuse is different. It is visibly, obviously, measurably dying. You can watch it change brightness with your naked eye over the course of months. You can see, if you know what you are looking at, the shoulder of Orion slowly consuming itself. It is also a reminder of something we rarely think about. The night sky is not permanent. We treat the constellations as if they have always been there and always will be, as if Orion and Scorpius and the Big Dipper are fixtures of reality as fundamental as gravity or mathematics. They are not. They are arrangements of stars at particular distances moving in particular directions at particular speeds, and they look the way they do because of when we happen to be alive. 100,000 years from now, the Big Dipper will be unrecognizable. 1,000,000 years from now, most of the constellations will have dissolved entirely, and on the shorter timescale of Betelgeuse's remaining life, Orion will lose a shoulder. The constellation that has anchored human mythology for tens of thousands of years, the hunter that Babylonians and Greeks and Egyptians and Aboriginal Australians all recognized and named, will be permanently altered. Not destroyed, but changed, diminished, one star short. And when it finally goes, whenever that is, the moment will carry a weight that no other astronomical event in history has carried, because we will have been watching, not just for years or decades, but for millennia. Aboriginal Australians encoded its variability into oral traditions 65,000 years before the invention of the telescope. Ptolemy noted its color 2,000 years ago, describing a yellow star where we now see red. Michelson measured its diameter a century ago, making it the first star other than the Sun to have a physical width. Hubble imaged its surface in 1996, the first direct portrait of any distant star. Dupree watched it blow off a chunk of its own face in 2020. Howell found its hidden companion in 2025. We have been staring at this star, studying it, arguing about it, and wondering when it would die for longer than most civilizations have existed. When the light finally arrives, when the neutrinos flood our detectors, and the point of light in Orion's shoulder blooms brighter than the half moon, brighter than any star anyone has ever seen, it will not be a surprise in any scientific sense. We have known it was coming. We have been waiting. And in the meantime, the star sits there, 764 times wider than the Sun, less dense than a thermos bottle, pulsating and churning and shedding and glowing, with a tiny companion star circling just beyond its surface, like a moth around a dying flame, a sphere of near nothingness, with a nuclear furnace at its heart the size of a small planet, wrapped in shells of progressively lighter elements, surrounded by an envelope of hydrogen and helium so vast it would swallow 5 planets and an asteroid belt, bleeding mass into space through winds and eruptions and convective plumes that approach escape velocity, plowing through the interstellar medium fast enough to create a bow shock 4 light-years wide, and carrying within it enough manufactured carbon and oxygen and silicon and iron to seed the next generation of planets that will form from its debris. It is not just a star, it is a countdown. And the fact that we cannot read the clock, that we cannot see through 3.5 astronomical units of convective envelope to the tiny core where the real timer is ticking, may be the most humbling thing about it. We have mapped the surface of Mars down to the resolution of individual boulders. We have detected gravitational waves from black holes merging 1 billion light-years away. We have photographed the shadow of a supermassive black hole at the center of a galaxy 55 million light-years distant. But we cannot determine whether a star in our own galactic neighborhood, bright enough to see with the naked eye, visible from any city on Earth during the winter months, is going to explode in 50 years or 50,000. The universe keeps its most important secrets well. You can go outside tonight, if the sky is clear and Orion is up, and look at the upper left corner of the constellation, the slightly orange one. That is Betelgeuse. That is a sphere of almost nothing, wider than the orbit of Mars, hotter than any furnace ever built, older than our species, but younger than most of the trees in an old growth forest, dying in slow motion at 548 light-years. Every photon that hits your retina left that star before Shakespeare was born. By the time you see it, the light is already 5.5 centuries old. What Betelgeuse is doing right now, at this exact moment, we will not know for another 500 years, unless, of course, the neutrinos arrive first.